Uh, very warm good morning to everyone. I'm Professor Manavendra Saharev. I'm an associate professor in Department of Civil Engineering. And first of all, I want to thank the Ministry of Rural Development, especially the NREGA division, who has been working with us for more than a year on this project. And when we started this work in April 2024, officially it started on April 2024, our objective at the time was to do a national impact assessment of Amrit Sarovar Mission 1, Phase 1, and also to develop some scalable tools that we can use for monitoring all the good works that have already been accomplished on the ground. So today I'll give a technical presentation on volumetric measurement and techniques in the project. The project name is Bhupahari. I think you can see it on that screen. Yes. So there are four components to this presentation. The first part is I'll talk about the project and the tools that we have developed. I'll give a demonstration on the portal that we have developed, where we have looked at all 69,000, but there are more ponds, but we have put in around 69,000 ponds in the portal already. This is a space-based monitoring system. Then we will look at the impact assessment of Amrit Sarovar ponds. And finally, we will give a hands-on demo how we are actually calculating the volume, because we also did field survey in around 15 ponds as a part of this project, mostly in Haryana. And we looked at DGPS, sonar, LiDAR, photogrammetry. So 4 kind of methods, and which methods are useful in which conditions, because not all methods actually work in all conditions. So which conditions are suitable, we'll look at it, and that is the part I'll hand over to some of my PhD scholars who are here today. Next slide. Yeah. So as Director Sir has already mentioned, India's rural water security is very important. I come from the water resource engineering section, and majority of the time when we are talking about water in a grand context, people are talking about rivers, people are talking about oceans, people are talking about dams, reservoirs, but majority of the people whose water security is actually determined by the water bodies that they immediately interact with. And that is where Mission Amrit Sarovar is making a big impact in terms of directly impacting people's life. But most of the time when we talk about water, oftentimes we talk about rivers and reservoirs. So I think this is an kind of under projected, but now it is increasingly getting prominence that we must, for water security to actually be realized at a rural household scale, we will have to rejuvenate and revitalize the water security at the village scale. This is what the project, the objective of the mission Amrit Sarovar is. As a part of this project, the primary motivation was that ground level verification is very tough. Right now, as far as I understand, there is a book that is maintained, like people do measurements on the ground, but there is an opportunity to develop and use advanced technologies that are available now for doing automatic measurements. So that is where it will give us very accurate assessment of what is the impact of the mission. Second, it will also help us to understand that if there is a requirement in phase 2, what can we actually plan? If there is an area that has not benefited in the phase 1, can we concentrate on that in phase 2? Or if some area has already benefited a lot, can we project that as a big success? So that was a objective, but only way we can do it is if we can do it at scale. So this was the project objective, in that to systemize and automate the monitoring of NREGA water bodies. But when I say NREGA water bodies, I always mean Mission Amrit Sarovar water bodies. And to develop a state-of-the-art framework for capturing the initial and final land profiles using ground and space to develop a framework and transfer to the ministry. So we try to divide the work. How can we actually think about this systematically? Now, there are 4 variables that is of interest to this mission. One is, of course, the surface area. The surface area can be monitored from satellite, but there are big challenges. But I'll go through it in the next slide. One is that we want to look at the surface area. Next is, can we look at the water depth? That is at the point scale. Now, the third variable that we are interested in is the bathymetry, the land profile. That means the transect along the pond, how we have dug it, if we have dug it in an optimal way so that it can store the maximum amount of water that is possible. And finally, of course, we are interested in the water volume. And the water volume is essentially, if we have a good assessment of point 1, variable 1, 2, and 3, then variable 4 is simply a mathematical exercise, a little bit of computation. In fact, we have developed a tool that we will show today. So this is kind of the methodological flowchart that we followed in the study. We have divided the ponds into four kinds of ponds. We looked at large number of ponds and we could slot it in these four categories. And this one is that one pond is under construction. This is all. This is a we are building it. Then type B is where it is already done, and we want to assess the impact in that particular pond. There may be water, there may not be water in the pond, depending on the time of the year or when the construction has finished. Then type C is, of course, where we are looking at renovated ponds. Now, why we are putting it in a different slot is that certain renovated ponds are quite big. They are a little bit easier to monitor. Now the pond is, if it is less than 1 hectare, that is what makes it very challenging, and I'll talk about how we have actually solved it. And part D is the most challenging one, that is the vegetation covered, because this is where all the measurement techniques have actually failed. Like one of them will succeed, and this is quite intensive. For example, lidar cannot penetrate through a vegetation covered area. Even sonar is very difficult, because if it is fully filled with vegetation, you actually cannot move the small boat on the pond. Today, of course, that problem will not be there when we show the demonstration in the evening. So finally, we have these four types of techniques that we use: lidar plus photogrammetry, sonar, and DGPS, Flagstaff. And we looked at all the three, and the final deliverable is, of course, the depth, the bathymetry, the volume calculations, and so on. Next slide, please. Next one. Yeah. So this is where it became a technical challenge. So we have been developing monitoring system for rivers and reservoirs for quite some time. But ponds are a completely different ball game, because most of the ponds are less than 1 hectare, or less than 1.5 hectare, 2 hectare. So many of the ponds are actually 0.5 hectare. And those are the kind of ponds we cannot see through a satellite, because a satellite has even the best available publicly freely available satellite can only do 30 meters, 20 meters. At most we can go to 10 meters. Now that is almost always bigger than the actual pond area, and there are always some errors around where the pixel will be located. So these techniques actually don't work for small ponds, even though they work for reservoirs. And we have done this extensively, that most of the time when we use the satellite data without any new techniques, then it will underestimate the water by almost 50-60%. So this is where so ministry gave us a list of lot of water bodies, 69,000 water bodies, and we went and manually digitized around 400 plus, roughly around 500 reservoirs, ponds. Amrit Sarovar ponds, we digitized it. Now, once we digitized it, it's fine. So once we digitized it, we fitted a machine learning model on the actual satellite band data rather than the image data. We fitted it on the actual bands. So there are 14 bands that come out of the European satellite called Sentinel. And once we combine it with the pond labels that we have manually made for 400, then this specially made model that is suited only for small ponds is actually able to do the surface area much more accurately. And this is where we validated with by going to Haryana in multiple ponds. Now, once we have trained it, so the flowchart actually shows the process that we get the Amrit Sarovar database from the ministry. Then we download all the data for 69,000 ponds. First, we do it for the 400 ponds, and then we manually digitize it, because that gives you the accurate surface area. And then we it's a relatively simple machine learning model, but it's quite effective. And you use the band data, and finally we get the surface area. Now, once you have trained the model, we actually run it on all the ponds that are available, and we have seen great results. Yeah. So this is the process essentially. The different ponds, they are, I've not put all the details, but they reflect different things. Certain things reflect the area, like the sand area. Some certain things look at the color. Certain things look at the different properties, reflecting properties of the water. So we processed around 600 GB of data all across the country. So this is the training. So once we have the synthetic aperture radar from satellite, we also have a co-located optical image. So optical image is what you can see through your eyes. The satellite can see through only during daytime. Then you have the synthetic aperture radar, the kind of satellite that can see through clouds as well. But they have limitations, is that they cannot see a very small area like a pond. But once we do this manual digitization, because this is a one-time task. It took us some time, but this is a one-time task. Once we do that, once we train the model, it actually works fine. Next slide, please. Yeah. So this is an example of what we found. This is a pond in Meerut, UP, and this was pre-construction in 2019. There was not much, and in 2020 there was post-construction. It was a new pond that was constructed there, and after that in 2024 there was renovation. I think sometime in 2023, I forgot the month, but there was some renovation during that period. Now, using our tool, we looked at what is the water surface evolution over time, and if you look at it, you can see the pre-construction the area is zero. The satellite is showing as zero. And if you go to the post-construction, the model starts detecting water and calculates the surface area, which is roughly around 0.5 hectare. Now, then we go to the post-renovation phase. This is where we go to 0.85 hectare. So now we have a very clear assessment that what is the exact value that has been brought in by the Mission Amrit Sarovar, this renovation work that has been conducted in this particular pond. Now, the same exercise, we parallelized it and we did it for all 69,000 ponds. And this is what led to the impact assessment part, that we looked at what is the total increase of surface area in the entire country because of this mission. Next slide. So we looked at 5 years of data for all 69,000 ponds, and ultimately we have a portal. This is a fully automated tool that downloads the data, processes the data, runs the machine learning model, gives you the surface area, and uploads it to the portal. So it's fully accurate, and it's made with the intention that large number of officers and field level functionaries are able to utilize it without needing to interact with all the underlying things that are going on. So this is the portal. Should we open now, or let's wait? Let's wait a bit. Let's go. I'll show you the portal in a little bit. I want to talk about the impact assessment part. So in the impact assessment part, we found out, now once we did it for all 69,000 ponds, we found out that around at 61% of the Sarovars recorded greater than 20% increase in average surface area. Now we have not even talked about the volume. We are simply talking about surface area, because once the surface area increases, the volume is naturally going to increase. But that we are seeing a greater than 20% surface area increase is itself a big accomplishment for this mission. So this is where we looked at which of the states have benefited the most in terms of increase of surface area. We found that Tamil Nadu had 91% increase in area that they had before the mission. So I think we took 2022 as the baseline. So all comparisons are between 2022 and 24-25. So average pond area in the entire country increased by 11.2%. Now there is a report as well that is, I think, circulated, and you will see a lot of other, this is just a summary, there is a lot more in the report. And you will see that there is a significant increase in average surface area that is observed post-intervention, with several states that are exceeding like at 100% growth. Next slide, please. Now, once we do that, one primary thing, and I think Director Sir highlighted that as well, that one important thing is what does it impact the water security? This is where the winter period becomes very important. Now, we found a very interesting thing that I don't think anybody has discovered it in any research paper till now. And I'm very glad that we now will be able to publish this work, because I think this will be exciting for people to know that because of this mission, the goals that there is a significant dry season gain. By dry season gain, we generally mean October, November, December, and January. So during this particular winter season months, actually from December, in this case, we have defined it from December to April. So this is where we don't have monsoon. In most part of the country, we don't have that much rain. But what we want to see is, are we able to retain more water than we used to? So the total dry season, I'm not able to read the number on the screen. So total dry season surface area has increased by, I think it is 16 million meter cube from pre-2022 to now 2024. And this is in the wet season, of course, it is easier to calculate because in the wet season, the ponds are generally full. In the wet season, we are seeing per pond increase by 58% nationally, but there are high performers in Tamil Nadu, in Madhya Pradesh, and Assam who have most benefited. But it also means that these places do get extreme amount of rain, which is able to fill up. In certain places like Rajasthan, there is a big increase in water, like ability to store water. but also these are very dry areas, so their overall capacity is anyway low compared to these states. So India saw an increase of 25 million meter cube in wet season pond surface area between 2019 and 2024. So these are not average. This is simply the increase, which is if you it's a very big number nationally if you think about it. That is now able to recharge the groundwater, hold water at a local area. So I think these are things that are very important to highlight the success of the Amrit Sarovar mission. Next slide, please. Okay, so before we go to the ground survey methodology, we would like to give you a glimpse of the portal. Yes. So this is the entrance to the portal. Essentially, right now it is at amritsarovar.iitt.in, but I think soon or maybe already it is will also be available through the BISAC portal, and then it will be available for everyone to access. And can we add the data? Yes. So you can go to this and you can add the data for any state. So let us add the biggest state. Yes. So now we can go to the particular, any random pond. Yes. Yes. So this is an example of a one pond where you will see the attribute table. The attribute table tells you that this is in certain location in Uttar Pradesh. What the attribute table is made from the ministry. So whatever information you already have access to, it is in the portal as well. But apart from that, you can also look at the evolution of surface area for any pond over the past 5 years. And going forward, we are expecting that we will just update it every month, and we will be able to monitor this from centrally. That what is the impact of this mission, and if some works have been, for example, sanctioned, how much is the progression of the work? Because we can do these measurements minimum 3 times a month. So roughly 3 to 4 times a month, we can get these numbers, the surface area numbers. So it is pretty. If the construction period is 6 months, we will get roughly 24 points to see what is happening on the ground. So this is this is a good pond. This is a area called in an area called Putkas in Uttar Pradesh, and this is a new pond that was constructed in 2020, but it also went through a renovation phase in 2023. And you will see that there is a very continuous increase of surface area in this pond. And this assessment that we have been able to do over the past 5 years, I think once we compile it and put it out in public, and I think people will also start seeing that there is so much benefit that has accrued to the public because of this mission. So now I would like to give you the demonstration. So now we have 3 demonstrations, one on photogrammetry and LiDAR-based method, one on sonar-based approach, and one is on the DGPS-based approach. So the basic thing is that LiDAR and photogrammetry is mostly we are doing it through the drones. And it has its advantages and disadvantages. Advantage is that you don't require any ground sensors. You can actually run it through a drone. The disadvantage is that you actually need a drone, and many of the Amrit Sarovar ponds are in very far off areas. So you may not have an easily accessible drone. In that case, what cheaper sensor can we use? So what we have found out is that sonar is the most reliable in terms of getting the depth measurements, because it's a very cheap sensor. The sonar sensor that we have tested with very expensive ones, but even the one that costs 20,000 is actually giving us very reasonable results. So this is something that the ministry can promote, and I think this is at the state level. I'll let you decide how you want to take this forward. So we will start the demo, please.
Good morning, students. Continuing on the presentations and moving on to the ground-based survey methodologies and the demonstrations. So, by seeing the data set that we were provided from the ministry and the different type of bonds, we made our methodology and we categorized the bonds. We had 4 categories for the bonds, and for all those 4 categories, we chose a set of working methodologies that would suit all the bonds. So we selected 3 methods. The first one was photogrammetry or LiDAR. We call it the drone-based method. The second one was sonar. It's a single beam sensor, and the third one was the DGPS Flagstaff method. The survey was done at 10 sites in Haryana, district of Jeen. So these are some important terminologies that we will be using in our presentation of the demonstrations. So going on with DTM. So a DTM, it's a digital terrain model. it simply shows you the earth, bare earth. That is, it includes the structures and the vegetations. And if we call it in the layman's language, it is the soil below your feet. As for the DSM, it is similar to a DTM, but it captures the topmost locations. As for the DEM, it is a digital elevation model and it is the most generally used elevation dataset anywhere. As for AVD, we use this term for the area volume depth relationship. It is a functional relationship that links our pond area, depth, and the water volume with each other. And the last term we'll be using is bathymetry. This is the mapping of underwater ponds or the bed topography. So the first methodology that we'll move forward is sonar. What is sonar? It's a sound navigation and ranging. It uses acoustic pulse to measure water depths, and it is mainly ideal for small to large ponds, but specifically with area larger than zero point 0.5 hectares. It provides a continuous and accurate depth once we sync it with the GPS, and it is one of the key tools in our Move Rahari Amrit Sarovar project. The minimum requirements for a sonar survey that we have given out are for the frequency range, it is 2200 kilohertz with the range depth of zero point 0.3 to 50 meters with a 5 centimeter accuracy. Along with the sonar, the minimum requirement, which is a must one, is a GPS device with a precision of 6 to 8 decimal degrees and obviously a portable raft or a boat for a stable deployment of the device. Along with it, we use the GIS softwares to process our dataset that we'll be showing in our demonstration. Now, talking about the equipment preparation and the calibration. So it is very important to have a calibrated instrument in your hand in order to get accurate results. So it is, we calibrate the sonar, we select a few reference points and we sync it with the GPS. And finally, once the georeferencing is done, we check for the battery, check for the storage capacity, and our instrument is ready to go. Now, coming at the survey design, it is usually advised to have a survey design in grids before going for the field work. Spacing required, you can select it as per the pond size. It is always suggested that you select a 1 meter block and move ahead with it. Coming to the field deployment, since we are doing the sonar for a water field pond, it is always supposed to be mounted on a board in order to capture water depth along the movement. Then, before, as I mentioned, you calibrate the device and then track the boat movement using the GPS, and then we record the values of the water depth below the surface. Now, after the survey on the field is done, we go forward with the processing of the data, wherein in short, we use GIS software. We convert our data recorded in, we convert the data recorded into a digital elevation model form, and then we create a bathymetry from that data set. And finally, we use that data set to estimate our area volume relationship and combining the compiling all the systems together, we get a continuous tracking system for every pond for which we can get the area, volume, and depth. Now, moving on to the case study that we'll be presenting today for the sonar. So, we selected a pond. It was in Sangatpura, Tehsil of Jind district of Haryana. So, it is a small pond, and it was completed when we did the survey on it. After the survey was done using the sonar and the processing was done, these were our results. Don't worry, we'll come to the demonstration after it and show you how the results were made. So moving on, like the results. So you can see on the screen the red line. It is the red line shows the elevation difference from between along the pond boundaries, and you can see that from our survey, we found that water surface area of this pond was 0.36 hectares and computed water volume was approximately 7,000 meter cubes with an average water depth in the pond that our experiment survey showed was at 2 meters. Now, the important thing here is how did we generate this DTM using the elevation model using sonar and how did we compute all these values? So this is the area volume depth relationship, and we will be showing to you how it works and how we conclude into it. Now, the most important part of the project was to combine all these informations in a complete single set of framework where we can dynamically track our area volume changes in a single pond using the earlier satellite tool that we showcased. So the first step, the final step that after the survey, after all the data processing, we always generate a area volume depth relationship, and this is generated from a ground-based survey. The next step is we extract the aerial temporal area time series change from the space portal that we have generated, that we have showcased right before this part. And now combining this space-based data with the ground-based data, we get a tracking system wherein we can generate how the volume has changed over this time by combining it with the area. So this way we have a complete setup for tracking area and volume changes over time. And why this system is better is because earlier we only used to have a water index that was being calculated, and the water index showed us, for this case, showed an area of 0.1 hectares, whereas our satellite tool, where we combined the machine learning with the satellite data, showed us an area of 0.38 hectares, and the field survey that we did showed us an area of 0.36 hectares. So it clearly resembles the underestimation of the pre-existing methodologies that was there, and dominance the superior methodology of machine learning. Yeah.
So I would like to add something, a bit more context to this. So in water and vegetation mapping, many of you are already interacting with space-based measurements, where NDVI and NDWI, these are normalized difference vegetation index and normalized difference water index, is very widely used, and they are very good for measuring big things. If you are interested in measuring a forest, if you're interested in measuring a reservoir, so they are quite accurate for those. But for ponds, as you can see, the numbers are quite off. If you, from the satellite only NDWI method, you are getting zero point 0.1 hectare, wildly inaccurate. So this is where the power and influence or importance of machine learning comes in, that we cannot just rely on satellite data. We have to combine it with more advanced techniques. And once you apply the technique, you can see that the actual surface area is 0.36, and we are almost very near to it. And since the purpose of the monitoring system is good enough tracking, not like centimeter level tracking, but good enough tracking, I think this is very useful for our purpose in terms of monitoring ponds. So now, and one another important outcome is that we only have to do this exercise one time. I mean, maybe in 5 years we have to do it another time, but for now, if we do it one time, we can get the volume measurements for this pond going forward. Because once we have the area depth relationship, this figure, tomorrow the satellite will continue to measure the area 4 times a month, 3 times a month, and you will continue to get the volume without, because we are always thinking about how to do it efficiently, because doing things very expensive way is quite easy. But we, in fact, that was one of the challenges presented to us by the ministry, that can we do it in a reasonable monetary like expense. And this is where we came up with this strategy that satellite is free. Satellite data we can continue to monitor, but ground data we can only do it once. So if we do it one time, we can continue to track the volume going forward. So that was the reason behind adopting this hybrid strategy, and I think it is quite successful, as you can see for this particular one. So I think we'll show a demo.
Moving forward, let me give you a brief about the demo. So there are going to be a few steps that we'll be walking you through. Okay. The first step is it's always after the completion of our field survey, we look at the raw data that we have. The first step would be loading our raw data onto the GIS software. Then further, for processing and generating a terrain model or elevation model from this data, we'll be using TIN-based interpolation. It's tin-based interpolation. It's triangular irregulated network. You could go for any other option if you like. You could go for IDW. You could go for cubic spline interpolation. It's as per choice. The third step, it would be after the DEM generation, we remove no data values by cleaning and filling in gaps. And further, we process the data using our area volume estimation tool and show you guys how the tool works. So moving on to the demo part. So let us start with the live demo. So first, let me show you the data which we get from the sonar instrument, that is the echo sounder. So we get the data in a CSV format. So let it just get open. and these contains three values. So first is the eastings, second is the northings, and third is the elevation. So we will be using the open source software QGIS for this demonstration, and we will be opening this data in this. So this is open, and we have to select the data that we get from the survey.
So since this data is in a CSV format, we use a delineated text layer add tool, which is available in the QGIS. We for
And
the
for text field, we will be selecting our eastings, and for the y field, we will be selecting our northings, and for the z fields, we will be selecting our elevation.
easting is the latitude, northing is the
And for the geometry, we will be
longitude.
selecting the geometry in which the zone of the survey lies, and we will be adding these points in the QGIS. So these are the points that we just got. And for the reference, let us add the base map. So this is the point base map, and these are the values that we got from the sonar survey. And we have to interpolate these points to get the bathymetry or the DEM of the base of the pond. So in this, we will be searching for TIN interpolation in the processing toolbox, which you can open from processing and toolbox. In this stage, we have to interpolate over our elevation values. So I will be selecting this elevation and then using the Z coordinate, that is the elevation coordinate for the interpolation, and then add this attribute. For the interpolation method, we can choose linear. For the extent, we can calculate it from our survey layer, that is the data that we have, and we can run this to get a rough DA, that is the bathymetry of the pond. And to visualize it better, let us change the colors. So this is our DEM, and these are the elevation values of the base of the pond, that is the bathymetry. And to calculate the volume from this bathymetry, we will export this, we will set the coordinate to the global ones, and we will export the data. So let us name this DEM, and then save, and then OK. So our file just got saved. So this is our file, and now we will open our volume calculation tool. And in this tool, we can go to volume calculation, and the DEM that we exported, we have to select this thing. So this is our DEM that we just exported, and as you can see that these are the contours which are generated from the bathymetry, and we can go to calculate volume step, load the same DEM here, and we have to just click on this start volume calculation, and the processing will be done automatically, and we can see that the depth is 1.40 meters and maximum volume that it can carry at this depth. And the same graph that we showed in the PPT, we can also like get this exported. So this is the demonstration for the sonar volume calculation. Now let us go with the PPT.
Okay, so the whole idea of showing you how to generate the DEM is to showcase how much the tool is automated. Once you have the digital elevation model generated at your step, you can simply use a tool to get the area volume depth relation from the tool. You could use the tool to get the water depth currently that is there, and you can get the tool to generate the surface area which is there at the time of survey. So now coming on to the next part of the methodology, the second part that we classified as the drone component. Herein we have two parts, photogrammetry or lidar, but the overall processing from the outputs is same. So we will be showcasing one of the demos for photogrammetry. So talking about photogrammetry. Okay, sorry. So first of all, we plan the drone flight path along the entire area of interest. This is important because we need to have a certain set of overlap while we take images from the drone. It could be kept from 50% to 70% based on the accuracy which is required. Then further, after having the images, we use photogrammetry technique to generate a digital elevation model. And in case of lidar, we simply get the DEM because that is what it records. Further, then from the QGIS tools, we again do the same processing, and using the DEM generated, we go for the area volume estimation using the AVD relationship. This is one of the videos of the on-field hands-on survey that we did. You can see our friend flying the drone. Now, coming for the equipment preparation and calibration, drones need to be calibrated using ground control points, and it is a must thing to do. Then, second, we need a GPS connection for the drone for georeferencing of the points, and it is always suggested to pre calibrate before the survey. As for the survey design, as I said earlier, flight path planning is must. You need to decide how the survey will be done along the test area. Coverage that needs to be done is 100% of the survey area that needs to be covered in the images, and the overlaps that can be kept is 50 to 70%, as I said again. As for the field deployment, we plan the survey flight. We operate the drone at 30 to 50 meter for optimal resolution height. Then GPS is continuously in connection with the drone. And after the survey is completed, we use the QGIS tools that we'll be showing in the demo. And from it, we get the surface model, we get the contours, but here's the catch: drones are a bit more expensive compared to the typical sonar or the DGPS methods, especially the lidar ones. But it is very accurate on the side as well. So why the question always comes in: if everything could be done from sonar and DGPS, then why do we go for photogrammetry or lidar? So my answer to this is not everything can be done from the DGPS or sonar, but having photogrammetry or lidar combined with it, it always yields out a more accurate result. Having an accuracy of zero point 0.1 to zero point 0.2 centimeters is always a good thing. So moving on, few strengths and limitations. The drone-based surveys, they have a higher resolution and a very high accuracy. It is fast and it is very scalable, and also it is ideal for dry conditions or even shallow ponds. The only limitation is that our drones, they cause a limitation when there is water in the pond, or especially when there is dirty water in the pond. And yes, flight permissions will always be required. So coming to the case study, we are showcasing the case study for photogrammetry. This survey was also done in the Jean district of Haryana, in a village called Dandakedi. So this was a pond where ongoing construction was going on. So it had no water, and it is, you can see in the image, it was still being dug up. So after the survey that we did for photogrammetry, and we generated our digital elevation model from it, we found that the total water area that we got was 0.56 hectares, and the possible volume estimate of the pond currently with the current dug up situation was 10,000, approximately 10,000 meter cubes, with the average depth that we calculated from the tool as 2 meters. So moving on to the demo for photogrammetry or the lidar, I'll give a brief and then we'll show you the demo as well. So after the since photogrammetry is clicking photos and moving ahead step by step, it's like having a lot of images and then generating a digital elevation model from those images. As you can see on the screens, the blue parts are the images that were captured, or the drone parts that were used, and the below it you can see the elevation model that is being generated from those images using the technique. The next step, the next step after this is running the tool and generating our digital elevation model automatically from it. combining it with the next step where we generate from the DEM area volume relationship, which will help us to move further. So moving on to the demo part.
So yeah, for this demo, I will be using the Metashape. So first of all, let me just get you the overview of the data that we get from the photogrammetry of LiDAR from the drone. So this is the data which is like captured, the aerial photos, and all of these photos are captured in one flat line. So if I just like move these photos, so you can see that drone is basically moving upwards, and whole area is scanned like this. So this is the data that we are getting, and we will be opening this thing in our Metashape. So let me just close this and then open it again. So we have to import all of these images. So we can just like simply drag and drop here and single cameras. And as you can see, this will automatically detect the position of each and every photos which are being captured. Okay, okay. So basically, we have just imported our photos, that is the raw data from the drone, and dragged and drop into this meta shape, and it will automatically detect every position of the photos which has been taken because each and every photo has its own latitude and longitude. And after we have done importing, we can simply audio was not clear. So after we are like done importing the images, we have to go to workflow and then we have to align the photos. So for the photo alignment, we can set the accuracy. Let us set high for now. And yes, and let us save this project. It will take around like 1 to 2 minutes of time depending upon the machine.
So this is done in order to align all the photos that we have taken from the drain in this sequence, and finally so that we can process it accordingly. The whole idea here is to click multiple images along the different path lines above a pond, and then using only those images we generate the elevation values from those images. That is what this technique is all about. And once we get the elevation model, thereafter everything is automated on the tool itself, so it's simply drag and drop on the tool. You can do the tracking.
So basically, this tool is Metashape. You can search on internet regarding some questions as we need to use it in Windows. As it is also available for Windows.
We selected the tools and the methodology in such a way that it is freely accessible and freely available for anybody who's willing to do it. All you need is a laptop with the software on it and just some ground data, and you can process the area volume and continuous tracking of that area volume using a tool itself with this methodology. So it's almost done. Once this is done,
So let us open another project which has been like already completed. Basically, what happens when the drone clicks the photos? So sometimes the alignment and all gets disturbed. So this step basically stacks all of the photos together in a particular flight line format. The accuracy for the GSD that you will be getting is around 2.5 centimeters. So as you can see, we got the tie points, and this is the, let me just zoom it a little bit more. So this is our area, and now we have to set the coordinate system. So go to reference, and after going to reference, we just click on convert reference, and we can select EPGS 4326, that is the global CRS, and then hit OK. Now the coordinate reference is set, and you can see latitude, longitude, and the altitude of all the photos which have been clicked. And at this step, we have to build the point cloud model, that is the 3D model, and from there, our DEM will be generated. So build the point clouds, and quality for this demonstration, let us keep this lowest, but you can keep it at ultra high or like high to get as maximum points as you want. So it will take around like some time, 3-4 minutes to complete.
Skip कर दे तब तक ये explain करते हैं नीचे cards क्या है.
Yes, we have the file. We have to cancel.
Cancel कर देना नहीं दिखाना है. Okay.
Should be fixed. Yes. Checkbox.
Yeah.
So as we need to use only Windows OS. Yes, this is based on Windows.
Okay. I think we can go from the beginning. Any questions? Mostly voice complaints. Um, I don't see many questions. I think align photographs. Okay. What is the tool that is used right now? The first tool that we used was QGIS. It's free software. You can also do it in ArcGIS. I'm assuming that through the ministry, almost all the states will have GIS licenses. You can do the exact thing in ArcGIS. We have shown it in QGIS because we want that the tools should be free. If there is someone who does not have ArcGIS, expensive ArcGIS license, they should be able to do it with this free. The second tool is Metashape. So this is a commercial software, but it has a free version which is sufficient for this task. So from day one, whatever tools we develop, we always make sure that there is always a free component so that even if you don't have a license, you should be able to do it. Of course, if you have a RGIS license, you can do this work anyway without requiring any free software.
Okay, so our processing is completed, and as you can see, we got our 3D point cloud model from the 2D images which are taken from the photos. And from this step, we can generate our DEM for this whole area. But before generating the DEM, as we can see, there are like lots of noise points which can color the DEM generation and can lead to the erroneous results. So first of all, we have to clip all of these points out to get as bare ground surface as we can. So there is a simple step to do this. So just like select some of the points that you don't want and just click on delete. So doing this thing, we have to do this for the whole area to get the full clear DEM. And we have already done this step, so let me load after doing that.
So this is for conditions where we have ponds. Oftentimes we have vegetation, even overhang over the ponds. So not all ponds will be as clean as this one. So many of the ponds that we saw, there is like vegetation, there is a half hanging tree. So all of those things, it's 5 clicks and you can remove it. But it is important to do because it slightly reduces the accuracy of the volume if you don't do it.
Okay, so this is the final DEM that we can generate from that point cloud model after clipping all of these keys. And we have to simply export this DEM, and we have exported that DEM here. And once our DEM gets exported, we have to open this thing on our volume calculation tool. So let me run this again. So our volume calculation tool got opened, and then click on volume calculation, and then we will load the DEM that we just generated from our point cloud model from the meta shape. So this is the DEM after clipping all of these noise points. And at this step, we have to clip the DEM which just contains the pond. Since you can see there are lots of structures, and we just need we just need the area on which the pond is there. So let me just do it roughly for now. Our pond is selected, and we have to clip DEM, and then we have to save this DEM. So let me save this DEM underscore, and our file got saved. After that, we have to go to calculate volume step, load the same DEM that we have clipped. So you can see the file is there, and this is our pond in this shape. And once this is loaded, we just have to click on start volume calculation. And as you can see, the volume got calculated for this area. And this is the area volume depth relationship. And the average depth that we got is around 2.78 meters. Now continue with the presentation.
So I think we have one final it's
Okay. So for
sorry, the question was not clear. So this measurement, because that particular this tool works for under construction ponds, because in under construction first you are dewatering anyway, so the pond is expected to be empty. In fact, that particular case study that I showed is an empty pond. I mean, by now it is filled, but at that time it was empty. So yes, this tool works only when the like because lidar cannot, at least the general lidar cannot penetrate through water. There are some specialized lidars can do it, but it is way too expensive to do it at scale. So we have not really proposed it as a solution, even though we have actually tested it. That is why we have proposed that sonar is cheaper to do, even though there are bathymetric lidars can do it, but they are quite expensive to handle and may not be feasible. Photogrammetry, you can do it before construction, during construction, but after construction, when rainwater comes in and the pond is already filled, then it won't work. That is when we suggest we use sonar. Good. Any other questions from anyone, please? Yes, we have standardized the methodology in a way that from all the three methods you will get everything, the same thing. The sonar that will work in the most diverse conditions. If it is vegetated, if it is shallow, if it is deep, it will work everywhere. But lidar it will work if your pond is empty. I mean, cheap is a relative term. How much you want to spend? Actually in places like Delhi, it is very cheap. Yeah, but we do it from the perspective that many of these ponds are located in so far off areas that you may not even have a drone available immediately in the field office. So we suggest things not from the Delhi perspective, but from the last mile perspective. Yeah. But it is actually quite cheap to do it in Delhi or any city really. What projects? Yes, I mean the whole demo has been shown for construction as well as renovated ponds. So before renovation, there will be dewatering, right? So during the dewatering process, you will anyway have to empty the pond, and at that time you can use LiDAR. But suppose for some reason there was not enough time, that the moment you dewater there was some rain event, then we can just switch to sonar. Sonar will work as even if there is water, it will work. So in that case, for example, if the objective is to only measure what is the increase in area, so suppose we generally will put some barrier and we will try to extend the volume of the pond. Yeah. So in that case, you can do the LiDAR only on the extended area. We don't need to do it in the rest of the pond. Then we can assess what is the increase in the surface area, or increase in the bathymetry in that particular location. But suppose you want it everywhere, then I think it is best to probably stick to sonar, because then it will work in all the conditions. And we also have a very simple method now. This is actually the simplest method, the DGPS one. It is quite manual, so we kept it at the last because it has a DGPS essentially fitted to a traditional Flagstaff. But all the other tools, that the tool that we have developed it in a way that you get the Flagstaff measurements with a DGPS attached to it, run it through the tool, and you get the volume. This will actually, maybe, I think this is something that you may be interested in, the DGPS. Let me go through it, and I think that might answer the question. It won't matter. It's meant for irregular shape. It doesn't matter if it is square, rectangle, irregular, anything. It will work. Yes. So the interpolation technique is not dependent on the size of the shape of the body. The interpolation technique is a mathematical technique. We call it triangular interpolation, simply to, like, it divides the area, imagines it like small triangles, then adds it. So it is an internal technique. It doesn't matter if the area is square or a rectangle or an irregular. The tin shape interpolation essentially is an interpolator for the DEM, the DEM preparation. But to answer briefly, it doesn't matter. The tin-based interpolation will work regardless of whether it is a square pond, circular pond, or whatever irregular size pond, mostly that we will have. Okay. Yes, that is a very good question. How can we, like, suppose we can get area, can we get a reasonable estimate of volume? So yes, we are able to do it because we have now 10, 15 points, and general AVD relationships can be estimated that if it is a 3 meter depth pond, average pond, what is the average volume? However, those relationships will never be that accurate. So we have not put it as an official recommendation in the report. So your suggestion is absolutely right, that we can get some baseline. Suppose your interest is in knowing that is the pond 5,000 meter cube or 10,000 meter cube, or 5,000 or 6,000. That we can do. But if your interest is in knowing whether the pond is 5,000 or 5,200, this relationship, this kind of, like, regression relationships won't give that accuracy. So we have not put it as a recommendation in the report. Yeah. Thank you. Let's go.
Okay, so moving on with the third and the final methodology, it's the DGPS flagstaff, or we say the differential GPS with a flagstaff. It combines the manual depth measurements with the GPS accuracy. It's definitely a reliable method and has been continuing from a long time. It also provides with to us a few centimeters level accuracy if we do the georeferencing properly. And it is usually beneficial where we cannot use sonar. Either where sonar sees some obstructions or some issues, we go for the DGPS method. And the minimum requirements for this is simply a DGPS receiver, the flagstaff rod, a boat or a raft to use it, a storage device, and further the noise limits that you can set as per your own requirements. Sorry. As for the equipment preparation and calibration, we calibrate the DGPS against the benchmark locations that we select on the site. We ensure that the markings on the flagstaff are visible from the DGPS. And last thing, we synchronize it with the GPS. As for the survey design, we again plan the survey in the similar manner. We select the grid points. We say that the minimum limit is to be kept at 1 meter, and we simply go along with the survey on the raft. So, as for the final fields deployment, summing up, we position the flagstaff vertically near the bed. We read the depths at a graduated scale, and then we move the DGPS staff along the pond water, and we get the values. Further, we process these values using again our software and the area volume depth tool, and we get finally the a real life centimeter level accuracy volume measurements as well as the water surface area measurements. Now for this, a few strengths and limitations. It works well where we cannot use sonar or photogrammetry. It works well when there's water. It is very cost effective as compared to the other methods, but a few limitations that is there. It is a kind of a laborious job. It is very limited in terms of a spatial resolution when we talk, and it is definitely a weather dependent thing, more weather dependent. Now, moving on to the case study, uh, we did this DGPS flagstaff survey in one of the, again, Jin districts pond. The village name was Ikas. So, after our survey, this survey we did for a combination of 5 renovation ponds that was being done there. We did a survey for all these ponds. We generated the elevation models for this combination of 5 ponds, as you can see. From this insights, we found that for one of the ponds that we will be showing this was the pond. So for this, we found that the calculated area is 0.26 hectares with the water volume at around 1000 meter cubes with the average depth of 1.2 meters. So moving on to the demo part, when we use a flagstaff survey, after the completion of survey, again we get the data in form of northing, easting and elevation levels.
So let us start with the temperature data of the DGPS. So this is the data, and as you can see, that it is same as that of the sonar. And we have like pretty much less points as compared to sonar because this is like manual job, and we have also like clip to keep this demo short. So eastings, northings, and elevation, these are our coordinates and the elevation values. So for this, let me use QGIS again, and let me open this. So we have to add the data from the DGPS. So this is our folder and this is our data. And in this, we have to set some of our fields. So for the X fields, we have set it to eastings. For the Y field, we have set it to northings. And for the Z field, we will set it to the elevation values. And this is our geometry CRS for that local area. So it is like predefined. And we have to add this data. And as you can see, our 7 points are like scattered in the So simply go to the processing and then toolbox, and then we will select search for the DIN interpolation. For this, the interpolation attribute will be the elevation values, and we will be using our Z coordinate as in the case of the sonar also. It will be same in the GPS. Adding this attribute, calculating the extent from our survey area, and then running this algorithm. So you can see we get a rough bathymetry DEM, and to visualize it better, let us color this. Once we get our DEM for the pond surface, we will export this thing. So this is for DGPS. So let me DEM, and we have to set the CRS to the global CRS EPGS 4326, and simply click on OK. So this is our exported DEM, and after this step, we have to again open our tool. Let me restart it. Go to volume calculation, load the DEM that we just exported. So this is the file, and you can see these are the contours, and go to calculate volume. And in this case, like, we don't have to clip this whole DEM because this is for the pond only. But in the case of that photogrammetry, we have nearby areas also, so we have to clip that area for to get just the pond. So we can skip this clip DEM step, and we can go straight away to the calculate volume. Load the same DEM, and once our DEM get opened, just click on this start volume calculation, and okay, our data gets exported, and you can see that average depth of 1.84 meters, and this is our ABD relationship. So basically this tool is same for all three methodologies, whether the pond is empty or it is filled or like it is under construction. The tool remains same, just the survey methodology gets changed. Now going back to the PPT.
Yes,
Yes, we have
into
to
the water.
insert it into the water pond.
Yeah, then we go for sonar.
So this particular method is only valid for one condition, where you have this vegetation filled pond, right? It's a very shallow pond. In fact, it is probably not a success story in terms of degradation. It is like fully filled with what we put this water hyacinth, and because of that, you can't even take a raft because the pond you can't take the boat, right? LiDAR won't work because it is filled with water hyacinth. So, and the pond is also not very deep because the rejuvenation work was not successful or it was not done. So this is only a backup method that is provided for the worst possible condition of the pond. This is not required to be used, but we have kept it because we found one pond where all the other methods failed. One or two ponds where it was filled with water ice. So we thought that at least we should provide some solution that if you are sending a survey team down, they should not come back with an excuse saying, oh, the drone did not work. So we should have a backup that, okay, if the drone did not work, at least let us go back with the more traditional DGPS FlexStop method and still get some decent volume, because then we can always take it in the next stage or however you plan. So I think completed this. So this is the, thanks for kind of staying with us. It was a very laborious presentation I had to go through, but I'm very happy that we could complete it. This is kind of a summary of all the things that we have shown, all the survey methodologies, which one is suitable for what. So this is kind of a checklist that we have provided, that if it is LiDAR, it is good for under construction depth and bathymetry. If it is already constructed, then for depth, for vegetated ponds for depth, but not for bathymetry. So if it is a photogrammetry method, so you can go through this matrix in your own time, and feel free to, like, there is a lot of information that we have summarized in this thing. But sonar is something that will work for all the areas, but we have only checked box one because there are other methods that are available. But sonar is, this is the, what we have said, this is the most accurate method. But sonar is something that will work for all of the conditions, or maybe for, like, we should turn it all to green just for clarity. So finally, we'll just end it here with the conclusions, saying that we developed this space-based tool, how to combine it with ground-based surveys, how to do the. We also developed a small piece of software that does this volume calculation for all four types of methodologies. You can use the same tool, and all the other things, DEM creation, you can rely on free tools. So of course, if you have ArcGIS, then you don't need to worry about this. Then hopefully, in conclusion, this was the report that was inaugurated by the honorable minister in the month of month of June. And finally, I want to thank the joint secretary. I think ma'am is not here today, and she has been a very supportive force throughout. And I want to thank director sir, who has been he is very actively involved, not just involved. So he regularly comes and really wants to know the technical aspects. So I'm very happy to work with him over the past period. And I want to thank both of the students who presented. They are PhD scholars in IIT Delhi in my lab. And of course, I want to thank everyone for letting us be a part of this mission. It was a great, for us, it was technical excitement because we could develop some new things. But the impact assessment part and the tools, if anyone has any questions, please feel free to approach us. And we are always available to develop things that can help our country, and of course help the country through you. So thank you so much.
Now, like request for the participants if they have any questions. Ankit, you can read out if any questions you have. And
Yes.
here in the hall, if you have any questions, please feel free to ask.
So first question is, I can just read the question and tell the answer maybe. So question is, could you kindly share the list of minimum tools required to carry out this process? We have prepared SOPs, and that will be circulated to everyone. So, and there are like 4 SOPs, 4 documents. All the minimum software, whatever is presented here, will be available to you. Second question is, please provide a link of Sentinel data link to download satellite imagery. I'm happy to provide the link, but we have done it in the way that you never have to worry about downloading the satellite data yourself. The portal does it in the back. Like, we have developed extensive amount of code to download the data, run the machine learning model, get the surface area in a format, and then upload it to the server. So, but anyone who is technically curious more, they want to look at the actual data, we will give you the link. Anything else? Oh, okay. So all examples taken from Haryana, usually free from flood and heavy rains, but for flood and water logging prone areas like districts of North Bihar. So this is a very good question. We are based out of Delhi, so Haryana was the nearest place where we could do this service. But the way I think about it is, the Bihar is a very flood prone area, and of Assam as well. But I think we are not going to do any rejuvenation assessment when we are in the middle of a flood event. So I'm not sure how to answer that question, but I think during a flood event we definitely won't be doing any ponds. But if the pond is filled to the brim, for example, flood event has receded and your pond is filled to the brim, the methods that we have suggested will anyway work. I mean, in the middle of a flood event, I don't know what to suggest though. But thank you. I think I've answered everyone. Thank you so much. Thank you.
Thank you so much, sir. Specification and video of this session will be uploaded in the P60 function model very soon. So, sir, thank you so much again to you and your entire team for this insightful session. Now, I think we need a little gap to cultivate all the information that we have received. So, I'd like to request all the participants to make their way to the reflection area and will read the name here and read the names. Thank you so much.